Hi, thanks for joining me. Today I'm going to be going over problem 2 from the second round of the Imperial College Maths competition from 2021. As always, I'll leave a link in the description below with details of the competition. This problem is a number theory problem, and as you can see, it's quite long. Let me read it out, I'll give you a chance to have a go at the problem, and then I'll go over a solution. Okay, so we have p being bigger than 3 a prime number, and we say that a sequence of p minus 1 integers, a1, a2, all the way up to ap minus 1, is called Wonky if they are distinct mod p. And they also satisfy this condition that ai times ai plus 2 is not congruent to ai plus 1 all squared mod p, and that holds for all I. And just to sort of account for the cases where I is p and p plus 1, we define ap to be equal to 1 and ap plus 1 to be equal to 2. We want to know, does there exist a sequence of does there always exist wonky integers a1, a2, all the way up to ap plus p minus 1, such that a1 times a2, a1 times a2 plus a2 times a3, a1 times a2 plus a2 times a3 times plus a3 times a4, and so on, all the way up to a1, a2 plus dot dot dot, all the way plus ap minus 1 times ap. All of these are distinct mod p. Okay, so if this was a bit of a mouthful, pause the video and have a go at reading the problem again, then have a go at attacking the problem, and join me in just a second and I'll go over a solution. Okay, so the answer to this problem is yes. No matter what prime number you give me, provided that prime number p is bigger than 3 or bigger than or equal to 5, I can always find a sequence of p minus 1 integers that are wonky. And I'm just going to show that by giving you sort of an example of p minus 1 integers. So what we're going to do is assume that all the congruences and stuff that I write down on the whiteboard are mod p. So that's just so I don't have to keep writing out mod p on the whiteboard. So what we're going to do is let ai be equal to the multiplicative inverse of I. So the multiplicative inverse mod p of I. And now what I'm going to first do is just check that it meets the ai times ai plus 2 is not congruent to ai plus 1 squared condition, mod p. So firstly, for I strictly less than p minus 2, so I being up to 1, I being 1, 2, 3, all the way up to p minus 3, we have the ai times ai plus 2. Well, that just going by this thing here is nothing but times I plus 2 and the inverse of that. But in particular, this is not congruent to if I add 1 to this guy here, which will give me I plus 2 plus 1 inverse. Okay, but if we just expand this out, we're going to get an I squared plus 2I plus 1, and that altogether is just I plus 1 squared inverse. Okay, and then just swapping the inverse and the squared, like so. This guy here, 1 over I plus 1 squared, well, 1 over I plus 1, or the inverse of I plus 1, that's just ai plus 1. Okay, so we have that ai times ai plus 2 is not congruent to ai plus 1 all squared, which is great, which is what we wanted to show. And the reason we needed I to be less than p minus 2 is because if we had I equaling p minus 2, then you can see this term here is going to be 0, and 0 doesn't really have an inverse mod p. So what we've got to do is just check the cases of I being equal to p minus 2 and I being equal to p minus 1. Let me just clear this up and we'll just check those cases. Okay, so let's look at the case I equals p minus 2. So ai times ai plus 2, what does that equal? Well, that's congruent to ap minus 2 times ap. Remember, ap is just a1, but a1 is just 1 inverse, which of course is just 1. So this guy here is nothing but ap minus 2. But ap minus 2 is just p minus 2 inverse, but of course this is just congruent to minus 2 inverse, like so. Now what about ai plus 1 all squared? This guy is just a p minus 1 squared, and this of course is just p minus 1 inverse squared, but of course we're looking at this mod p, so this is just minus 1 inverse squared, so this is just minus 1 all squared, which is 1. And definitely 1 is not the inverse of minus 2, so this shows that this guy is not congruent to this guy. Okay, so now in the case I equals p minus 1, we're going to do the same thing, compute these two guys here. So ai times ai plus 2, well, that thing there is just ap minus 1 times a p minus 1 plus 2, which is p plus 1, but that's just a2. So we have this guy here, and now p minus 1, or just plugging it back into the definition, this thing here is p minus 1 inverse times 2 inverse. But again, p minus 1 is congruent to minus 1 mod p. So this guy here is nothing but minus 2 inverse, like so. And what about ai plus 1 all squared? Well, this guy here is just, in the case I equals p minus 1, this is just ap squared. ap is just a1, which is 1. So that's 1 squared, which is 1. And again, we get minus 2, which isn't congruent to 1. So we get that ai times ai plus 2 is not congruent to ai plus 1 squared. Great. So we've shown that if we define ai like this, it meets our second condition. Now what we've got to do is just check it meets our first... it meets our first condition in that they're all that ai times ai plus 2 is not congruent to ai plus 1 squared for any I. Now what we've got to do is just check that the final sort of sequence of numbers are distinct mod p. So a1 times a2, a1 times a2 plus a2 times a3, and so on all the way up to a1 times a2 plus ... plus a p minus 1 times ap. Okay, let me clear up the whiteboard and we'll show that. Okay, so I've defined sk to be the sum from j equals 1 to k of aj times aj plus 1, and that's for k being 1, 2, 3, all the way up to p minus 1. So this is essentially what we had before written at the bottom of the statement of the question, but here I've just written it in summation notation, and what we want to do is show that each of the sk's are distinct mod p. Okay, so firstly let me explicitly compute what the sk's are, and then show that they're different mod p. Okay, so firstly we'll consider when k is less than p minus 1. So essentially when k does not equal to p minus 1. What do we have here? Well, sk is equal to the sum from j equals 1 to k of aj times aj plus 1. But remember how we defined aj and aj plus 1. This is just j inverse times j plus 1 inverse, which of course is just j times j plus 1 inverse. Okay, but I'm going to write this in sort of fraction notation. So this is congruent to the sum from j equals 1 to k of 1 over j times j plus 1, because remember we're looking at everything mod p. But now what we can do is use partial fractions to write this thing here as the sum from j equals 1 to k of 1 over j minus 1 over j plus 1. Okay, just check this thing equals this thing. Let's multiply both the top and the bottom of this thing by j plus 1 and the top and the bottom of this guy by j. So we're going to have j plus 1 minus j, which of course gives 1 on the numerator, divided by j times j plus 1. Great, so going from here to here is valid. And now this guy here is telescoping, so if you just write out perhaps the first few terms and the last few terms, and we'll see that all the middle terms will cancel. So this is congruent to 1 over 1 minus 1 over 2, so that's the case j equals 1. When j equals 2, 1 over 2 minus 1 over 3. Then we're going to get a plus 1 over 3 minus 1 over 4, and so on. And anyway, we're going to get up to our last term, which is 1 over k minus 1 over k plus 1. This 1 over k will cancel with a minus 1 over k in the previous term, so all we're left with is a 1 over 1 minus 1 over k plus 1, like so. Okay, so for k being less than p minus 1, sk is congruent to 1 minus 1 over k plus 1. Now let's quickly check what happens in the case k equals p, and then we'll show that they're all different mod p. Okay, so now let's compute sp minus 1. Well, of course, because it's just summation, it's the same thing. It's sp minus 2 plus ap minus 1 times ap minus 1 plus 1. So in other words, this guy here is the same thing as sp minus 2 plus ap minus 1 times ap minus 1 plus 1, which of course is just ap, like so. Sp minus 2, well, we just worked out, is congruent to 1 minus 1 over p minus 2 plus 1. So this guy here is congruent to 1 over 1 minus p minus 1. And then ap minus 1, remember, is just 1 over p minus 1. And ap is just a1, which is 1. So these guys cancel out quite nicely. So this is just congruent to 1. So sp minus 1 is congruent to 1. Now what I'm going to do is show that each of the sk's are distinct mod p, and then we'll be done. Okay, so now we just need to check that all the sk's are distinct mod p. Well, it's quite clear to see that sp minus 1 never equals sk when k is less than p minus 1, because obviously if they did, we'd have 1 being congruent to 1 minus 1 over k plus 1 for some k less than p minus 1. But then, of course, that would mean that some inverse of some number was 0, which doesn't make any sense. So this guy can never equal this guy, so we just need to check this guy never equal. So for any two k's less than p minus 1, so sk and sk tilde, say, aren't congruent mod p. So suppose k and k tilde are less than p minus 1, well then, and they're distinct, sk is going to be congruent to 1 over 1 minus k plus 1, and sk tilde is going to be congruent to 1 over 1 minus k tilde plus 1. But it's quite clear to see that these are not congruent, because, or not the same thing mod p, because if they were, then we'd have the inverse of k tilde plus 1 is the same as the inverse of k plus 1. But remember, inverses are unique mod p, so that's impossible unless k and k tilde are the same. And that solves our problems. We've shown that we've essentially found a sequence of Wonky integers which satisfies the definition of Wonky, and that such that each of these SKs are distinct mod p. Anyway, I hope you have enjoyed this video. Do check out my solutions to the other problems as well. There'll be a playlist, probably a link in the description below as well. But yeah, thanks for watching. I'll catch you in the next one. Have a great day.